What's up, guys? Welcome back to another Algebra 2 final exam review session here with Mr. Gaines as we look at our Units 1 through 10 review in this series of videos. Let's jump right into some example problems. So in problem number 6, it says, which of the following could not be a solution to the below equation? So in here, we have a few different options. We have an option that x could equal 5, 4, -8, or none of these. Potentially x could be all of those answers. And that would give us a solution of none of these. So for instance, in this problem, we could try to find the correct answer, the correct solution or solutions to these equations. But a quicker way to identify which one could not, emphasize not, be a solution is to take a look at what the domain would need to be. Remember, with rational expressions or fractions, you cannot have a 0 in the denominator. So if I take a look here, if I put in a 4 there, that would give me a 0 in the denominator. If I put in a 3 there, that would give me a 0 in the denominator. So right away, I can identify that x cannot be 4. This could not be a solution. X cannot equal 4 because that would give me a 0 inside the denominator of this expression, and thus it would not be part of the domain. Let's go ahead and take a look at number 18. 18 is another example of rational expression work here. It says, which of the following represents the below expression in its most reduced form? So here we see a subtraction of two fractions. And remember, in order to subtract fractions, you need a common denominator. So what I'm going to do is take a look at the factors of the denominator, and to each fraction multiply by the missing factors, if you will. So in this first fraction, I can multiply by x over x to give me a denominator of x times x minus 1. In the second fraction, I'm going to multiply by x minus 1 over x minus 1 to give me a denominator of x times x minus 1. And while doing so, I'm going to also multiply in the numerators and simplify. So I would distribute here and get minus 2x minus 2. Now remember that I'm subtracting the second fraction, so I can go to the point where I would like to combine my numerators. The denominator would remain the same, x over x minus 1, and this would be 3x minus the second fraction's numerator, which is 2x minus 2. So notice that I did put that second fraction in a set of parentheses as a grouping because we were subtracting the entire numerator, the 2x and the negative 2. So this would be 3x minus 2x, which would be 1x. And the negative here would be 2, so positive 2x plus 2 if I distributed. So that answer would be C. Another rational expression in 19 says, which of the following represents the below expression in its most reduced form? So remember here, I can eliminate factors of fractions. So if a factor matches in the numerator and the denominator, the fraction can be reduced. So if I look at the numerator, I may notice that there's a GCF of 3x. So if I remove the 3x, factor out a 3x, that would be a better way of explaining. If I factor out a 3x from each of the terms in the numerator, I would have 2x squared minus 3x plus 1. Then here, my 3x in the numerator would divide with my 3x in the denominator, and so I would have the remaining expression 2x squared minus 3x plus 1. And if I take a look at the expressions that are listed, it's close to C, but doesn't exactly match C, so this is actually going to be none of these. It's not going to match any of those options. The correct answer would have been 2x squared minus 3x plus 1. Problem 20 says to identify the holes of the below rational expression. Well, remember, holes are restrictions on the domain of a rational function. And in order to find restrictions on the domain, we have to take a look at the denominator, the factors of the denominator. So if I factor the denominator, it factors into x plus 1 and x plus 3. This means x cannot be negative 1 and x cannot be negative 3. Again, as we saw in problem 17, you cannot have a 0 in the denominator. So if I put a negative 1 in there, that would give me a 0 in the denominator. If I put negative 3 in here, that would give me a 0 in the denominator. So both of these are restrictions on the domain, but this specifically asks for holes. Holes occur where factors of the numerator match factors of the denominator. So I have a factor of the numerator that matches the factor of the denominator, which could in turn be simplified, but this would give me the whole. So my whole would occur at x equals -3. That is the domain restriction that matches in the numerator and denominator. Let's take a look at some more examples. Problem number 21, we get into logarithms. It says, which of the following would be an equivalent expression to common log base 10 of a minus log b equal to c? So we have a variety of options here. Now let's think about some things that we could do here. If I use my properties of logarithms, I can combine these two logarithms. So using one of those properties, it tells us that when I subtract two logarithms with the same base, their input values may be divided, a over b. And that would be equal to c. And I don't see anything that is exactly this written so far. So let's try to simplify it a little further. Remember that the base of the logarithm here is 10. So I could write this into an exponential equation if I would like. Base 10 of c is equal to a over b. And I do find that expression at answer D. So here I combine the logarithms through my properties of logarithms, my quotient property, and then rewrote it as an exponential equation to find the expression that matched in 21. In 22, it says, which of the following is equivalent to the expression x equals log base 3 of y? So kind of thinking along the same process of the previous, I can't really combine anything here through logarithmic properties, but I can rewrite an exponential form. So this would be of base 3 to the x power equal to y. Remember, the inputs and outputs of a logarithmic and exponential function switch because they are inverses of one another. And so the rewritten form would be found there as part A. In problem 23, it says a river in upstate New York is decreasing in depth by 3.5% each year. Which of the following functions represents the depth of the water d with respect to t years? Well, remember that if we are increasing or decreasing by a certain percentage, this is an exponential growth equation. So I can use my exponential growth formula, which you do have in your notes if you need to refer to that, as q of t is equal to q sub 0 times the quantity 1 plus or minus r to the t power. So in here, I'm going to go ahead and substitute in what I know. I don't know a q sub 0, that would be at my initial value. So I'm going to leave that alone for right now, or I could replace it in this case with the notation d sub 0, if I would like. My r would be the percentage point, or 3.5%. But remember, when we change this into or put this into a problem, I need to change it into a decimal. So 0.035 is my decimal. And I don't know how many years, so this would be to the t power. Now remember, this water is decreasing, so I actually need to do a subtraction here. So over on my calculator, if I would like, I can take 1 minus 0.035, and then I get the expression 0.965. So simplified inside the parentheses would be A. 0.96 d sub 0 times 0.965 t to the t power would represent a 3.5% yearly decrease. In problem 24, I see some similar concepts here. It says the half-life of propofol is 38 minutes. Which of the following represents the amount of the dose still active in the system 1.5 hours later? So what I'm seeing here is a kind of a percentage decrease. Half-life represents percentage decrease. And we're going to change the units. We want to go from minutes to hours. So remember that changing the time domain is affects the exponent. We can see that in the equation written above at 23. So let's let m represent minutes, and let's let h represent hours. And I'll show you kind of the written out work, and you could get here a little bit faster. But if I want to have 38 minutes, that would be m to the 38th power. This is the half-life, so the percentage that would remain would be 50%, or 0.5. So what I can do here then is take this down to a minute. 1 minute would be 0.5 to the 1 over 38 power. I could take the 38th root of both sides, but that's the same as you doing the 1 over 38 power. Now, if I want to put this in hours, This is 1.5 hours later. So let's go ahead and convert this to minutes. This would be 90 minutes. So if I want the 90 minute, here's the first minute, what the percentage would be decreased on a minute by minute basis. If I want m to the 90th power, I would take this expression 0.5 to the 1 over 38th power, and then take that to the 90th power as I'm changing the time or the exponent. So I can do this in the calculator. I'm going to go ahead and combine my exponents and write it as 90 over 38. And this would give me the percentage that would remain active in the system 90 minutes later. So remember, if I want to convert this into a percentage, I want to move the decimal over 2 places. So that would be approximately 19.4%. Let's go ahead and take a look at another example. Now we're getting out of multiple choice into some short answer, or what would be like our part 2 questions. So in problem number 5, it's 25, it says sketch a graph to represent x is greater than 4 or x is less than or equal to negative 12. So in this case, we're wanting to deal with a number line. So I'm going to go ahead and sketch out a number line here. The 2 important numbers in my number line are going to be negative 12 and 4. So x is greater than 4 would represent anything to the right of, but not including 4. So I'm going to have an open circle at 4, and I'm going to shade to the right. And this is going to represent anything greater than 4. Less than or equal to negative 12 would be a closed circle at negative 12 because we are including negative 12. And then I would shade anything to the left. So because this is an or statement, I'm going to have 2 distinct places on my graph that are shaded in. In problem 26, it says create a set A and a set B such that A and B, or the intersection of A and B, is negative 1, 0, and 2. So again, as I read this initially, this could be the intersection of A and B can also be read as A and B. So what I need is I need a set for A and a set for B where the numbers that they both include are negative 1, 0, and 2. So I could make A negative 2, negative 1, 0, 1, 2. It doesn't really matter what else is in there as long as I have negative 1, 0, and 2 that will also be included in B. So let's say I have B is negative 3, negative 1, 0, 2, 4. So this would be a good example. Your example could be entirely different, but this would be a good example of sets because the terms that they have in common in each of the sets are negative 1, 0, and 2, and only negative 1, 0, and 2. Problem 27 says James solves an inequality and lists his answer as r is greater than or equal to 3 and r is greater than or equal to 6. It says based on this, James states that the answer must be no solution. Do you agree? And explain your answer. Well, let's take a look at a number line. Let's start there. And on the number line, my important numbers are going to be 3 and 6 based on this information. So if I wanted to shade first greater than or equal to negative 3, I'm going to have a closed circle at 3. Sorry, greater than or equal to positive 3. I'm going to have a closed circle at 3, and I'm going to shade everything to the right. Now the symbol and means I need to include overlapping sections of the 2 statements. So r is greater than or equal to 6 would be shaded to the right of 6. So here you can see where I shaded twice. That's really what's thicker here on the shading. What I shaded to twice was everything to the right of and including 6. So we would say that no, when r is greater than 3 and r is greater than 6, this implies r is greater than 6 because any number greater than or equal to 6 is also greater than or equal to 3. So here it's asking for numbers that are greater than or equal to 3 and greater than or equal to 6. Any number greater than or equal to 6 is also greater than or equal to 3, so it satisfies both conditions. So the answer, no solution, would actually be incorrect. Taking a look at another example, here we have a graph in 28. It says use the graph of f of x shown to the right to answer each of the following questions. Is f of x a function? Hopefully you can look at this graph and say, yes, that it is a function. It is a function because the graph passes the vertical line test. And what this is checking, and it is good to know what the vertical line test, I'll abbreviate for VLT. It passes the vertical line test. What this is checking is, does each input correspond with only one output? Does each x value correspond with one y value? And as I take a vertical line here, I can find that through this graph, there's not a location where one input has more than one output. Thus, that meets the requirements for a function. It says, if f of x is a function, it is. Determine if it is even, odd, or neither. In this case, we would say that this is neither even nor odd. To be even, it must have symmetry about the y-axis. And we can see here, let me go ahead and draw in a line. We can see here that on opposite sides of this line, it is not symmetric. Or if I reflected across the line, it would look something along the lines of this. It would not map directly onto one another. It can't be odd as well, because odd functions must have rotational symmetry about the axis. So let me pick a single point here. The point 2, 0 would then must exist at 0, 2, and it does not. And so this does not have odd symmetry as well. So this is neither even nor odd. It says given g of x is the negative f of x plus 1, determine if g of x is even, odd, or neither. Well, this is a good question here. What we need to do is consider the transformations. So this would be a shift to the left 1 and a vertical reflection. So if I wanted to kind of get an idea of what that would look like, a shift left 1 would put the vertex here, and a vertical reflection would put it there. If I continue to move some points, I'd have a shift left 1. A vertical reflection would keep that point there. I'm going to take this point at 2, 0, shift it left 1. Vertical reflection would keep it where it's at. And what we would start to get is a shape of a curve that would, or a parabola that would look like this. And so, not the best drawing here, but this would be even. This would be an even function. As we shift it left 1, it is now centered on the axis, on the y-axis, and thus the parabola would have a reflectional symmetry across the axis. Find all solutions for f of x is the request in f of x equals 0 is the request in D. So let me get rid of the graph that I just drew in here for g of x. F of x equals 0. What I would be looking for is any y value that is 0, or specifically in this case, the x-intercepts. So I have two locations where x equals 0 and x equals 2 that would satisfy these conditions. In problem E, part E, it says find the average rate of change across the interval -1 to 2. Remember, average rate of change can be found as change in x over change in y, or change in y over change in x, or y2 minus y1 over x2 minus x1. So the x interval I'm given here is between -1, x is -1, which we have the point here, -1, 3, and x is 2, which we have the point here, 2, 0. So if I want to do this algebraically, I can input the y values, 3 minus 2, over the x values, -3 minus 0 would be our y values, over the x values, -1 minus 2, and this would give me 3 over -3. So the average rate of change, the change in y over change in x, would be -1. You can also see that by taking a look at those 2 points here, and I can see that this, if I were to count on the graph, I could see that this shifts down 3 on the y-axis while shifting over 3 on the x-axis. So again, negative 3 over positive 3 would be negative 1. Let's take a look at one more example here, problem 29. In problem 29, it says complete each of the following questions with respect to the function shown below. So f of x in this example is a quadratic function. Now we're going to have some graphing components to this, but also some algebraic components. So first it says to list the y-intercept. Remember, the y-intercept is any location where f of x is equal to 0, or where f of 0, where x is equal to 0. So the y-intercept is when on the on the y-axis when x is 0. So I can substitute in 0 for this and very quickly find out that the answer is 6. And so I can find that without graphing. In part B, it says to algebraically find the x-intercepts. So algebraically means I'm going to need to show an algebraic process. Remember, x-intercepts are when f of x is equal to 0. So what I can do here is set the equation equal to 0 and then solve. Now, in solving this equation, there's a variety of different ways that I can do this, but it's probably easiest to try to factor. Factoring is a quick process here. I'm going to do so by getting rid of my fraction. Most of us don't like to work with fractions, so I'm going to multiply both sides of the equations by actually a negative 2. So if I multiply the entire equation, I'm multiplying the entire equation by negative 2 to make sure that I get rid of my fraction, and also to change my leading coefficient to positive. Factoring generally gets easier in that case. So I would have x squared plus 4x minus 12 equal to 0. So here I may try to factor this. And in factoring it, or looking to factor, I would see that this has an x and an x, because my coefficients would need to be factors of negative 12. One has to be positive, one has to be negative. Factors of negative 12 that would, through distribution, give me a 4x would be 6 and negative 2. Then solving here, I would get x, setting each equation equal to 0. You can show that work if you would like. So set both factors equal to 0 and then solve. I would get x equals negative 6 and x equals 2. I'm going to need to sketch the graph of my function eventually, so I'm going to need those points in a little bit. Algebraically, find the vertex. So there's a couple of different ways that we can find the vertex algebraically in part C. We can rewrite the equation into vertex form using completing the square. But a shortcut, if you remember back to earlier this year, is to find the vertex using the vertex formula. So the vertex is hk, where h is equal to negative b over 2a, and k is equal to, in this case, f of h. So what I could do here, if I want to find the vertex, I could do negative b, and I'm going to go back to the original value of my equation here. Negative b would be a negative 2, so positive 2, over 2 times a would be negative 1/2. So 2 times negative 1/2. So this would be 2 over negative 1, which is negative 2. Then k would be to find f of h, or f of negative 2. And I'm going to go ahead and do that in my calculator. So my calculator, if I input this equation, substituting x as negative 2, I'm going to get a y value. And this would be the y value for my equation. So the vertex here is going to be negative 2, 8. So now I can draw or graph my quadratic using some of these features in part D. So what I can do here is I can find the vertex and go ahead and put the vertex down at negative 2, 8. This is a parabola that opens down. We know that because the leading coefficient was a negative value. I'm also going to have x-intercepts of negative 6 and 2. I'm going to have a y-intercept of positive 6. I could sketch in here my axis of symmetry. It's not required. It doesn't necessarily ask for it, but we could put that in there. And then I would have some points to draw my parabola. You could also work at, or use your graphing calculator here to help you draw that parabola. Let's go ahead and take a look at the table. And I'm going to scroll over here, first starting at -6, could have -6, 0. And then I could go to -5, 3.5 if I wanted to here. To get a sketch, so -5, 3.5 would be about right there. And then I have the point -4, 6 in here. I could have -3, 7.5. So kind of starting to fill in some of those gaps. And I could use my graphing calculator to do that. You don't necessarily have to, but that would give us a little bit better of a path to draw in the curve. And so I want to make sure that it goes through all of those points. So after we find the locations algebraically, we can use those locations to help sketch the curve as well as the graphing calculator. And this looks like a good place to kind of finish part 2 of our review. If you want to look at more questions from the finals exam review, take a look at part 3. As always, thank you guys for tuning in, and I'll see you.